Good afternoon, all. In the previous session, we have completed the relationship between the directivity and maximum effective aperture with the help of this figure, which you can see it on the screen. Considering the two different fields, EA and E suffix R, which is at a distance R, we have seen what is the relationship between D and AEM. This box what I have put, okay, this is the relationship. Then based on this, what we have done, we have tried to calculate for two practical antennas the AEM value and the directivity value. Okay, the first practical antenna for which we have calculated these are, it is the short dipole antenna. This we have already covered. Important thing to remember, this is the picture taken for a short dipole. You can see this is the feeder part. These are the two poles. Okay, the same diagram. Important thing to remember here is current distribution is constant. Current I is assumed to be constant. So very directly based on this basic equation AEM, we have got this equation while dealing with the maximum effective aperture V square by 4PRR. Here V value we have substituted directly E into L, because L is the length of that antenna and E is the field. As the current is constant, the field will be same. So because of this, V is very much straightforward, E into L. However, in today's session, we will be discussing regarding the maximum effective aperture and directivity for lambda by 2 antenna, that is half wave antenna. Okay, the difference between short dipole and half wave antenna is, in case of short dipole, it is very much general. The length is less than its wavelength. Okay, here what is the length? It is very much specific. It is lambda by 2. If this condition is met, then it is half wave antenna. Okay, here half wave antenna, it's a dipole antenna having the length of the total wire equal to half of its wavelength, that is L equals to lambda by 2. That you can see it here in the figure. Feeder, then these are the two poles. However, the length is lambda by 2. If you observe these dotted lines, what it indicates here also, if I think it's not very clear, from pencil I have drawn, this is showing the current distribution. Okay, so it is current distribution. I naught is indicating the maximum value. Okay, uh, so in earlier case current was constant. Here it is distributed in the form of a sine. Okay, in the form of a sine. Hence the equation changes a little bit. Okay, so let's see what changes. How we started the equation in the first derivation, we started with this equation. Okay, here also we should start with this. We will go for substitution of this V, P and RR, just like this. Let's move to this second derivation. This is the figure considered. Okay, what all to be explained in the figure? Very first thing, let us consider a half wave antenna with the terminal resistance RT. In earlier it was RR, RT equals to RR. Okay, then we will equate it, no doubt. Then length is lambda by 2, and the incident wave, it is in the minus negative x direction. Okay, it's similar to that. You can see it here. I have written a plane wave incident on an antenna, it is traveling in the negative x direction, right? This is positive x, so negative x is opposite of that, negative x direction. Let the wave be linearly polarized. I hope you have seen the image or the GIF which I have sent in the Google Classroom for linear polarization. There are three different types. The three figures are very clearly shown: linear, circular and elliptical. How the wave gets polarized in these three different formats, I have shown you in that GIF. With E in the y direction. So if you see, the field distribution will be in the y direction. Okay, that is E. Okay, E is in the y direction, and the equivalent circuit is as shown. Here it is shown to you. Now, if you observe this figure, let me just take so that it is both is visible to you. The small voltage dV, if not for complete, okay, only a small portion for this circuit, it is actually the voltage induced by this particular incident wave, because wave travels the power generation, and the due to the voltage the power generation occurs. Okay, so voltage gets induced by this incident wave. That is because of what? Because of out of this complete length, only a small part dy we have considered. So a small infinitesimal length, elemental length of dy of an antenna. Because of this particular smaller element out of the total length, we have got a smaller value of the induced voltage. Okay, now we have to consider a lambda by 2 dipole which is placed along y-axis. Okay, this is the y-axis direction. Now important part is, see what I have done here. This I have written it first, but don't go like that. What you do, first you write this. Maximum effective aperture, we know that it is given by this. You put this equation number 1. After that, what we will do, we will try to substitute for V. For that, this is the explanation. Okay, but I have taken first V and then this. Don't do that. First write the equation 1 and then we will go for equation 2. Now, what we will do, the field distribution with respect to origin is this. Why it is not simple E? Because current is not constant. Because current is not constant, the distribution of current is in the form of sine wave, that is sinusoidal. So it is E cos omega t. Okay, cos or sine, you can take however it is. So E cos of omega t. If you observe, instead of omega t, I have written something here. How I got this? I got that term, I have written here. Omega t is equal to 2 pi f into t, or 2 pi into frequency is c by lambda, c into lambda. Is it right? F equal to, I think I have written it wrong. F equal to c by lambda. Yeah, c equal to f lambda, correct. F equal to c by lambda, and the time is given by, how you get the time? This is the velocity c, velocity of light, is equal to the distance traveled divided by the time. So what is the time? Time is equal to y by c, y by c. I hope you understood this. Let me explain you once again. I think I have written this wrongly. F equal to c by lambda. Okay, there should be a slash in between. Then c equal to, speed is equal to, velocity equals to distance traveled, that is the distance of the antenna, that is y by t. So t is equal to y by c. I have substituted that, and for frequency c gets cancelled. 2 pi by lambda into y you will get. Why we want to convert this? Because the known parameters are for our antenna design, it is lambda and the distance y. Because of that, instead of writing omega t, we are trying to convert it into known parameters. Okay, this is about the field E. Now once this E is known to you, now assuming this, now whatever we have calculated, this is now constant throughout the element. We know that a small portion of the voltage, it is due to this, whatever the small portion of the induced voltage dV, it is due to a small element dy. If you consider dy as a small length, according to your equation, V equals to the field into L. Field just now we have calculated, it is now E, small e, this one, which is again in terms of cos. small e into length, small length we considered is d into y. So in earlier case, this we have directly substituted. Now instead of e, we have to take small e. Small e is in terms of cos, and the length is for small length, small dy. dy is equal to dv is equal to e into dy. Once we get this, now this is small voltage induced due to a small portion of the element dy. If we want a total induced voltage or the total potential difference, we have to integrate this term. Integrate this over what? What is the total length of your antenna? The name suggests it is lambda by 2. So either you have two possibilities: take the range directly from 0 to lambda by 2, or I can take from 2 times 0 to lambda by 4, or from minus lambda by 4 to plus lambda by 4. It's according to your convenience. You can take this integration limit. You can take 0 to lambda by 2 directly also. Why I have taken this 0 to lambda by 4? Because if you see the structure, how I have put it is along y direction. If the total length is lambda by 2, the center position is exactly at the origin. So this is lambda by 4, this is lambda by 4. So 2 times lambda by 4 I have taken. Okay, that is the reason. You can directly take 0 to lambda by 2, no issues. So with this range, small e, just now we have seen it is the sinusoidal distribution. So it is e cos of known terms 2 pi by lambda into y, and the differentiation is with respect to dy. After this, 2 is kept constant, e is also constant, take it outside. Now what is the integration of cos? It is sine of 2 pi by lambda into y. Apply the limit 0 to lambda by 4. Now what is the coefficient of y? It is 2 pi by lambda. So you have to multiply by 1 by 2 pi by lambda, right? It will become lambda by 2 pi. Why you have to multiply? If you have, say, integration of cos of, say, 2y, then it will become sine of 2y, and the coefficient should be divided. So that coefficient I am writing 2 pi by lambda here, 1 divided by that. It is lambda comes to the numerator. Now further simply solve it. 2e and lambda divided by 2 pi. 2 gets cancelled. E lambda by pi will be outside. Apply the limits lambda by 4 in both. The lower limit is 0, so this will vanish. Second term will vanish. The first term you will get sine of pi by 2. Sine 90 is 1. So voltage induced is this. Earlier it was very simple. Voltage was E into L. Directly we substituted. But here we have to consider this small e because of the sinusoidal distribution of the current. So new value of E will be in terms of cos. So that's why the induced voltage is not very simple. It is in terms of E into, it is not L, it is lambda by pi. Okay, this is one equation. Then we have this already. In this V we have just now calculated. Now we should go for P and RR, two unknowns. So for terminal resistance, as I told you, we have to assume that RT and RR both are equal and there is no loss. So with that, RT is equal to RR, and RR value for a lambda by 2 antenna, it is 73 ohm. Again, you have this concept in the next chapter where you will be proving this 73 ohm. Okay, and even this also in the earlier what you have considered, RR equals to 80 pi square L by lambda. Even this you will be proving. Okay, both RR values for short dipole and lambda by 2 you will be proving in the next concepts. Then V is over, RR is over. What is P? P is the power density or the Poynting vector E cross H, or E square by 120 pi. We are preferring to get the value in terms of E square because here we have E term. So we can say, we can do something about it. Now you have got equation 2, that is V. RR and P. Substitute all these in your maximum effective aperture. What value you will get? See, AEM is equal to V square divided by 4P RR. RR is 73 and this I have substituted, and this is square. Okay, E square gets cancelled. E square gets cancelled. Then 4 ones are 4 30s are. Then out of pi square, 1 pi gets cancelled, denominator. Remaining are, this denominator of the denominator 30 will come to the numerator, and you have lambda square here, lambda square as it is. 1 pi is left out from pi square, that pi, and 73 ohm. So with all this, if you calculate this value 30 divided by pi into 73, you can check it, you will get 0.13. What was the value we got in the earlier short dipole? What was AEM? Can anybody?
0.119.
Yes, it was 0.119 lambda square. Here it is 0.13 lambda square. We got both the values, and once we have got AEM, it is easy to find directivity because we have already derived this relationship, directivity and AEM. Directivity is given by 4 pi by lambda square into AEM. AEM, I will just take one step above, easy for calculations. I will just substitute that. Let's see what gets cancelled. 4 pi lambda square gets cancelled. Then pi gets cancelled. You'll be left with 4 into 30 divided by 73. If you calculate this, you will be getting somewhat around 1.63. What was the directivity value earlier for short dipole? For a short dipole, it was 1.5. And now we have got directivity as 1.63. Okay, so you have to remember both the terms. Excuse me for, yeah. So we have seen the AEM, maximum effective aperture, and directivity for two different practical antennas. One is a short dipole, the other one is half wave antenna. Okay, any doubts here in this derivation? Earlier it was very easy, it is V equals to E into L because current distribution is constant. In the second case, as it is sinusoidal in nature, you should go for a cos or a sine. Okay. Any doubts you can ask me, put it in the chat box or unmute and ask me, else I will move to the next.
No, ma'am.
Okay. The next parameter is effective height. Can we just have a listing of how many parameters we covered till now? This is one of the parameters. I'll just show you the screen. It is easy for you. How many parameters we studied? Okay, we started with the first one, this power density. The first parameter we studied is power density. Then we went for patterns. Then beam area, that is beam solid angle. Then we have seen few problems. Next, radiation intensity, capital U. Okay. Then directivity, capital D. In directivity, we have seen after directivity, gain, capital G we have seen. Then directivity and resolution, and antenna apertures, five different apertures we have seen. That is effective aperture, scattering aperture, loss aperture, collective aperture, and physical aperture. Okay, in antenna apertures, we have seen this. This is one relationship which we derived in the previous class. Then the Aem and D value for two practical antennas. And then the next parameter is effective height. Okay, now we are at this antenna parameter, effective height. Just like effective aperture means, if you have this much of area, out of this it may be that due to some losses and all, only this much is useful for us. Okay, this whatever shaded part is there, that may not be useful. That's why effective aperture will be lesser than the actual aperture. So it's similar to that. Even effective height will also be the same. Okay, out of the total height of the antenna, maybe due to some losses or some reasons, the total height, the total length of the antenna may not be used effectively. Okay, or always effective height will be lesser than the actual value. That's what I said. I have given you the example of a pineapple. If you get the pineapple from the market, it will be of 2 kg. When you cut it, when you just peel the skin, and the useful part will be only 1.5 kg. It is like that. It will always be less than the actual value. Now coming to the next parameter, effective height. The effective height of an antenna, it is related to the aperture, as I said. Multiplying the effective height by the incident field E will give you the voltage induced. This you know it already. V equals to E into L, right? So if you multiply the height, that is here in your equation, it is length, height by the incident field will give you the voltage induced. So V equals to E into, instead of L, height has been considered, H. So V equals to H into E. So accordingly, effective height, how we can write? H will be equal to V divided by E. That is the ratio of induced voltage to the incident field. H equals to V by E. Now, this is general equation for effective height. Now let's see for a particular practical antennas how it will be less than the actual height of the antenna. Now, if you take one example, this is the just previous example which we have calculated AEM for lambda by 2 antenna. If this is the field distribution, as I told you, it is a sinusoidal distribution. If you take the center point, this is actually, the view is, you can take this, flip this. The view is like this now. Just rotate it 90 degrees, you will get this view. So the center part will be your maximum value. If you just start from 0, 1 is the maximum. And if you take the average value, it will be, I think average value for sinusoidal, you have calculated all these in rectifiers, half wave and full wave average values. It comes to be 2 by pi. You can cross verify it. That is 0.64. Okay, so this is the average value for this sinusoidal distribution. That's what is marked here. You can see just the figure is flipped. 0, this is maximum point, this is 0.64. So if the current distribution is uniform and the effective height would be what? L, total length. Uniform hota hai current distribution, so directly you will take the complete length as its height, that is lambda by 2. But however, what is the current distribution? It is sinusoidal. Because of that, the average value will be 0.64 times the maximum. Hence, your effective height will be not equal to L. It will be 0.64 into L practically. So 0.64 times L means it will be less. Okay. If you take length as lambda by 2, say length as say 4, some example I'm taking, you L equal to 4, what will be the height? 0.64 into 4, how much you will get? What is 0.64 into 4?
2.56.
2.56. See, actual length is 4, but you are getting 2.56, which is less than the actual height. Okay. This is one example. Now, taking the second example, it is again the same dipole it's there, but the wavelength this time it is zero point 0.1 times lambda. That is, length is not lambda by 2, it is lambda by 10. Okay. So if that is the case, now how I got this? See, if I have 2 points like this, if I say this is a sinusoidal distribution, if I increase this, something like this, if just I keep on increasing this, looking from this end, this looks like a straight line. Looking from this end, it looks like a straight line because as the distance increases, this curve, okay, it is it appears to be a straight line from this end and a straight line from this end. That's why these 2 points, it is not a sinusoidal here, it appears to be a straight line and coming and joining at the center. It looks like a triangular distribution, not the sinusoidal distribution. This is because we have assumed length as lambda by 10, not lambda by 2. Okay. If this is the case, the distribution will be triangular. Okay. I have given you the example. If 2 points you consider, keep on increasing the distance, the distribution, it appears to be a straight line. Looking from those two ends, from this end one straight line, from this end another straight line. Don't imagine on a paper, imagine on a earth, on the earth, two different points. As you increase those 2 points, what will happen? If you are the observer at those 2 points, the sinusoidal distribution looks like this to you. Okay. So the current tapers almost linearly, that is a straight line I said, from the central feeding point, okay, to O at the ends in a triangular distribution. Now the average value for triangular distribution, it is half of the maximum. I don't know, you just verify for triangular wave what is the average value of the voltage or a current. You please google it and check it, okay, for sinusoidal and for triangular, for both you can verify. It appears to be half of the maximum. In earlier it was 0.64 times the maximum. Because of this, earlier case effective height was 0.64 times L. In this case it is 0.5 times L, half. Okay. Even though length is 4, your effective length, height is 4, effective height will be 2, the useful part. Okay. This is about the effective height. Generally the equation is simple, h equals to v divided by e, but however if you take two examples, the effective height for these two examples appears to be lesser than the actual height. As a note I have written here something, check it. Relation between effective height h and aperture AE. Yes, because the first line what I started in the effective height is related to aperture. Okay. This, let's try to prove it, how it is related to the aperture. Okay. For an antenna with the radiation resistance RR, the power delivered is given by this, W equals to V square by RR. This you know it, P equals to VI or V square by RR or I square by R. Okay. Now if you take I square into R, this we have already seen in case of aperture calculation. We have taken one equivalent circuit, RR, RT and RL, real part, and the reactance part, XL and XT. Okay. This we had got as the magnitude of the current. Remember? So substitute this, you will get, instead of I square, so W will be equal to V square by this denominator. So V square divided by denominator square. Square and square root will go. So simply bracket terms will remain and numerator RR term. Then For maximum power transfer, Rr is equal to Rt. There will be no loss and this reactance term will go. That's why you equate these two with a negative sign. Rr equals to Rt, that is terminal load resistance what you have is equal to antenna resistance, and there is no loss. If you substitute, you will get W is equal to V square into Rr, numerator, denominator is 2Rr whole square, or V square into Rr divided by 4Rr square. So I think Rr and 1Rr square out of it will go. V square by 4Rr is the power. Okay, W is equal to V square by 4Rr. This is the important equation. Okay. Now, this we have seen. The voltage induced is equal to E into L, that is E into H. So, what we will do, in this W is equal to V square by 4Rr, V value we will substitute, that is H into E. Okay. Let us substitute. It will be H square into A square because it is V square divided by 4Rr. 4Rr as it is. This is one power radiated. Okay, one equation. Similarly, if you go to this we know it, power density is E cross H, power radiated per unit area being perpendicular. This is the definition of power density. With this, W will be equal to P into A. Okay, and if you take the effective aperture, it will become AE, and P is, that is E square by 120 pi, E cross H, 120 pi. 120 pi, I have written it Z naught in general. Z naught is the intrinsic impedance. Impedance value is how much? You have already seen. It is 377 something ohm, that is 120 pi. Okay, E square by 120 pi. So this is also a radiated power. This is also a radiated power. Equate both of them. If you equate this equation, H square E square divided by 4Rr, and this E square divided by Z naught into AE. E square gets cancelled. H square is equal to AE divided by Z naught. AE is divided by Z naught, and denominator 4Rr will go to the numerator. So you will be left with, this is for H square, take the square root. 4 will become 2. I have done any mistake? No. Remaining is only this much to be put in the square root. This is H is equal to 2 into square root of this. This is the relationship between H and AE. Or what you can do, take this equation, try to find the equation for AE. So AE is equal to what? H square Z naught divided by 4Rr. So you can write in both ways, just like Aem and D. You can express AE in terms of D or vice versa. So this is the relationship between AE and H. So in the today's class, we have seen the Aem and D value for lambda by 2 antenna and the next antenna parameter, that is effective height. So any doubts till this? Please let me know if
No,
you
ma'am.
have. Okay. So in the next class, we will be dealing with one important derivation, that is a freeze transmission formula. Okay. It is no doubt anywhere it is not a parameter, but however, this freeze formula will give you the relation between the radiated power from transmitter. Assume that this is your transmitter and this is your receiver antenna. So whatever powers, say assume this is your WT and this is your WR, transmitted power and received power. So this freeze formula, FR double I, yes, FR double IS is the name of the scientist. Freeze formula will give you the relation between these two powers in terms of these antenna apertures. Aperture AET indicates for transmitter, AER indicates receiver. So freeze transmission formula will give you the relation between the radiated powers transmitted and received in terms of their apertures and in turn gain values GT and GR. Okay. So in the next class, we will be dealing with the freeze transmission formula. Fine.